Hey guys, what's up? Welcome back to the classroom. It's Mr. Low, and today we'll be going through the third part of the wave series. Right, so remember for part 1, we talk about general wave property. In part 2, we discuss about sound wave, which is a longitudinal wave. And in this last part of the 3-part series, we're talking about electromagnetic wave, which are transverse waves. Okay, so let's get right into it. So electromagnetic wave, or EM wave for short, is a family of many types of waves. So it's a family, and there are many types of it, and it starts from radio waves and it goes all the way to gamma rays. So there is a whole spectrum of it in between. They are together called electromagnetic wave because fundamentally they are made up of an electric field and a magnetic field. They are propagating together in space. Okay, so this part is not very important as to what's the relationship between the two of them, but just know that it is a family of them. Okay, so so there are 7 components that you need to know. So you have the radio wave, microwave, infrared, visible light, UV, X-ray, and gamma ray. So you have to memorize these names, and there's a particular sequence that you have to memorize them in. Okay, so I'll show you what is the sequence in the next page over here. Okay, so when we arrange these electromagnetic waves in the sequence from radio wave to gamma ray, we are arranging them in terms of increasing frequency and decreasing wavelength. Okay, so I say again, from radio to gamma, we're looking at increasing frequency and decreasing wavelength. So that just means that for radio wave, it has the lowest frequency but longest wavelength. Okay, for radio wave. Yeah, so it has the lowest frequency but the longest wavelength amongst the whole spectrum of electromagnetic wave. On the other hand, at the other end, gamma ray, it has the highest frequency but shortest wavelength. Okay, so I'm using lambda to represent wavelength as usual. So this is how we structure them. So the names, if you look at the second line, I have a mnemonic for you to help you to memorize. If you go and Google out there, there are many types of mnemonics aimed to help you to memorize RMIVUXG. You can feel free to come up with your own, whichever helps you. Okay, but you're supposed to memorize the names in this particular sequence. Yeah, okay, sure. Again, you see this formula popping out again. Again, this is general wave equation. So all waves, including electromagnetic wave, they obey this equation. So from the chart above, you saw that the differences between each class of wave is the frequency and the wavelength, which are all related to each other in this equation over here. Now, amongst all of them, they have different wavelengths, they have different frequencies, but there is one thing that is common. One thing that is in common between all the 7 classes of electromagnetic wave is that the speed is the same. They all travel at the same speed. Okay, so looking at this equation here, all the wave have the same V. So you know the math. As frequency goes up, the wavelength goes down. Vice versa, right? As the frequency goes down, the wavelength goes up. So you can see as a result, radio wave having the smallest frequency has the largest wavelength. On the other end of the spectrum, gamma rays, it has the highest frequency but the lowest wavelength. Okay, so the only thing that is common between them is that the speed is the same. And what is that speed? Actually, is the speed of light. Later we come to that. Okay, so amongst this spectrum, you see this part in the center called visible light. This is the usual light that we can see with our naked eyes, which is actually the rainbow colors, ranging from red all the way to violet, right? So the light that we can detect with our eyes travel at the speed of light, and so do every single class of wave in this electromagnetic spectrum. Okay, so they have a different range of wavelength. So each class of electromagnetic wave has a range of wavelength and frequency. Doesn't mean it's just a fixed number. Okay, so do we have to memorize all of this? Definitely not. We do not have to. What we need to be aware of is our visible light spectrum. It's between 400 nanometers to 700 nanometers in terms of the wavelength. Okay, so for 400 nanometers, which is the longer one, okay, later you will see in the picture below, as shown here, 400 nanometer is for red light. But, sorry, should be the other way around. Let me erase this. 700 nanometers, the longer one, is red light. But 400 nanometers is for the shorter wavelength, violet. So I'm using this color. This is not exactly violet, but just using this to represent violet. Okay, so your visible spectrum, which falls in between UV and infrared, it is a spectrum of different colors that you can see with your eyes. So it's from 400 to 700 nanometers. Okay, and that's the only thing that you need to know for this portion here. Yeah, so if we go back to the different classes of electromagnetic wave, right? So starting from visible light to the side that has higher frequency, you have ultraviolet. So the way that I like to remember this is the last part of the visible light spectrum is violet, right? So I use this color over here. This is violet, and away from violet you have ultraviolet. On the other end you have the color red, and beyond red is infrared. So it kind of helps you to match the names to the colors, okay, on one end of the visible light spectrum. Okay, so again, the main important thing is all of them travel at the same speed, which is the speed of light, which I'll tell you what's the number later. Okay, so all electromagnetic wave, they fall under the same family, the same class of the same spectrum, and they have similar properties, okay, compared to each other, besides their speeds. So number one is that they are all transverse wave. So remember, in your syllabus, the only longitudinal wave that you need to know is sound wave, which is the previous chapter. Okay, so the rest, you can safely assume they are transverse waves. Next, electromagnetic wave, they can travel through vacuum. So this should remind you of your thermal radiation. Remember, between conduction, convection, radiation, radiation is the only one of the three modes that can pass through vacuum. And vacuum has no material at all. Okay? So similarly, your whole electromagnetic spectrum can pass through vacuum. In fact, I think I mentioned this quite a few times. Thermal radiation is actually your infrared wave, which you see in the whole spectrum, this guy, infrared. So this guy is your heat radiation. Okay, so this guy is in charge of a heat radiation. So it is part of the electromagnetic spectrum. It can pass through vacuum. Number three, just as all waves do, they transfer energy from one point to another. They do not transport material. Okay, they do not transport matter. They transport only energy. Right. Next, we talk about the speed that every class of the electromagnetic spectrum travel at in vacuum, which is the speed of light, 3 times 10 to the power of 8. Just as a fun fact, Albert Einstein, he came in to say that this speed of light, 3 times 10 to the power of 8 meters per second, is the ultimate speed in the universe, which means nothing in the universe can travel faster than this speed. And in fact, only light or anything that has no mass can travel at this speed of light. Okay, so the whole spectrum, starting from radio wave all the way ending at gamma ray, they all travel at 3 times 10 to the power of 8 meters per second in vacuum. If he has to pass through a different medium like water or glass or whatever, his speed will slow down accordingly. Okay, so this number only applies to vacuum. And last but not least, they all obey this general wave equation, as I said earlier. Well, by virtue because it is a wave. right? So in case you forgot, let's just recap again. This V is the speed. For EM wave is 3 times 10 to the power 8. F is for frequency, shorthand. Lambda is your wavelength. Okay, so this equation has appeared in the past 2 chapters as well. You should be very familiar with it. Okay, so when, just now I mentioned, right, the 3 times 10 to the power 8 meter per second only applies in vacuum. When it enters another medium, say glass, its speed will change. You recall from lower sec, chapter 5, remodel of light. Light bends when it enters from one medium to another because its speed slows down. So when it enters a medium or a material of higher optical density, it will tend to slow down. Okay, so the thing that changes here is the speed, but the frequency does not change no matter which medium it enters. So when it enters glass, what happens is its speed change, but the frequency does not change. So as a result, because of that, the wavelength changes. Okay, so it is the wavelength and the speed that changes, but the frequency does not change when it enters from one medium to another. Right, and then just now I mentioned about ray model of light, chapter 5, in your lower sec, you have reflection, refraction, the law of reflection, so on and so forth. Okay, it is obeyed by visible light that we can see. It is also obeyed by every single class of electromagnetic wave, okay, in the whole spectrum. So whatever you learn about properties of reflecting, refracting for light, it also applies to waves like gamma rays, radio wave, microwave. They all behave in a similar manner. Okay, so now I move on to use the formula, the general wave formula, to show you how we can test you in this chapter. So it's a very typical thing, right? I give you either the wavelength or the frequency and you find the other. So example here, UV wave. Okay, UV light has wavelength of 400 nanos in vacuum, while microwave has wavelength of 1 mm. So 2 different wavelengths. Okay, calculate the frequency of each of these wave. So looking at UV first, its wavelength is 400 nanos. So for V equals F lambda, okay, the V is the speed of the microwave, which I said earlier is 3 times 10 to the power 8. Okay, for any electromagnetic wave. Then I just substitute in my wavelength. Remember, nano means 10 to the negative 9. This is for nano, and you get a number. Likewise, for microwave, the speed is also 3 times 10 to the power 8, and then I substitute in the 1 millimeter, 1 mm for the wavelength, and I get different frequencies. So you can see after this calculation, if I do compare the frequencies, okay, for UV ray is in the range of 10 to the power 14, while microwave is in the range of 10 to the 11. If we go back to the spectrum and we compare, we see that comparing UV and microwave, is it microwave? Yes. Comparing UV and microwave, you can see that UV is at the higher frequency portion. So this is consistent with what we've already learned. Okay, so this is just an example. So again, all EM spectrum wave travel at speed of light. Okay, so you can try this example yourself. I did not put in the answer to that, my apologies. We'll go through again when we come back to class. Yeah, but basically, what you're supposed to do is, I give you the frequency, you're supposed to calculate the wavelength, and which type of EM wave is it. So again, I'm still using the formula V equals F lambda. You plug in the appropriate numbers. We are looking for wavelength. This is the unknown. And what is the speed? You should know. Okay, so it's a very simple example. Pause the video and try it for yourself. Otherwise, the last part of this very, very short chapter, we're looking at the real-life applications of different classes of electromagnetic wave. This is commonly tested in the form of MCQ, or even in structured, we can ask you to list 1 or 2 uses for each of these electromagnetic wave. Okay, I'll not go through this in detail. Basically, you can just read. Okay, and I would advise that you memorize perhaps one or two common ones that you see, that you may know of. So maybe things like for radio wave, radio and telecommunication, yeah, this broadcasting thing, this is what I advise you to memorize. Microwave, this one you already know. This one you can memorize. For infrared, this one because it is the thermal radiation, so you can memorize this. This is commonly tested and appeared. So these three. So for remote controls and intruder alarms. Okay, so intruder alarms basically they detect the infrared coming off your body, right? So it's like a night vision kind of a thing. Okay, visible light, this one very common, you should know. For UV, we use it to sterilize equipment. It is also used in, this is also pretty common. Okay, pretty commonly appeared in questions. For X-ray, definitely your imaging, and your CT scan is also quite common. Okay, for gamma ray, because they are high energy wave, very high energy. Basically, the higher the frequency, the higher the energy. So this gamma ray and X-ray, they are high energy in nature. So as a result, long-term exposure will result in cancer and other health issues, right? So this is also used in sterilization. It is also used in radiotherapy for cancer treatment. Even though it kind of causes cancer, but it has high enough energy to destroy tumors and cancer cells. So it has to be a targeted treatment. It has to be aimed precisely at the spot where the cancer cells are detected. Okay, so these are, whatever I think are those that I recommend you to memorize, about 2 per type of wave. And that's it for this video. It's a really short chapter. There's nothing much. It's a bit more memory work than the rest. You only have one main formula over here, of which then the speed is a fixed number. Also, the number 3 times 10 to the power of 8 meter per second, it's kind of like a common knowledge, but we do not require you to memorize. We will give it to you if we need you to calculate in the question. Alright, so that's it for this chapter. I'll see you back in class. Take care.